тише, говорила с ним об этом еще потом. И вечером я уже успокоилась, и такая, вот, здорово сейчас поговорить, но тогда не получилось.
Ничего не Тимур, у тебя микрофон включен. Выключи, пожалуйста.
Hello.
Так у нас лектора еще нету в Zoom.
А у нас лекция.
Может забить 100 человек до того, как придет.
Okay, ladies and gentlemen, can you hear me?
Yes.
Yes. Yes, wonderfully.
Oh, by the way, it's not possible to have a lecture because host disabled participant screen sharing. So let me think about that. Maybe I can do something. Okay.
Привет. А, вы с одного смотрите?
У тебя включен звук.
Меня? Не понял.
У тебя, по-моему, включен звук.
А у меня включен звук или нет?
Ну, сейчас включен.
У меня вроде выключен, да, ребят?
Да,
У меня
да,
выключен звук сейчас.
включен.
Понял, спасибо, парни.
Да не за что.
А лекции пока нет.
Звук
У
есть.
Евгения Дашкова звук просто не включен.
Twitch будет?
The problem is as follows. It is not with my sound, but with screen sharing. Screen sharing is disabled by the host. So it is not possible to use a whiteboard.
А,
Told you, like, you might
May-
actually just rehost the
you can host.
chat and that's all.
I'm not the host. I don't know the code, so it's quite
You can create another one.
another one. What?
We can go to Microsoft Teams.
Another one Zoom. Короче, конференцию еще одну создать. DJ Khaled.
Руслан, у тебя еще звук был включен.
Да пускай поет классно, что.
Согласен. DJ Khaled. The best music.
Another one.
Паша, ты вообще кидок, мы с тобой не разговариваем.
Что?
Что договаривались в библиотеке на 3-м, 4-м. Вот, а ты где? Дома.
У меня библиотека здесь.
Ну ладно, приходи к нам, Виноградин.
Я на 4-й поднимусь только.
Я дома.
Все в порядке? Олег, а ты дома?
Нет. Я в офисе на работе сейчас нахожусь.
Сейчас дня, ты до сих пор не дома. Давай быстренько.
Паш, у тебя звук включен.
По-моему, у тебя тоже звук включен. По-моему, у всех у вас, пацаны, звук включен. А, да, я не знал, кстати. Спасибо.
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 Да не за что.
Спасибо.
Сейчас включен или выключен, я не понимаю, просто я не знаю как. Я не в зуме первый раз просто. В смысле не в зуме? Да нажать. А, ты же в офисе.
Выключено.
Ребята, если что, я не в зуме, я сейчас в Teams сижу.
Ты в
Слушай
офисе,
через
да?
Teams. Не, я в Teams.
Microsoft Office.
Нет. PowerPoint.
О,
Okay, I have found the key to claim host, so everything should be okay now.
Hello.
Okay, so let's begin. Can you hear me?
Yes.
Yes,
again.
we can.
Yes, we can.
yes.
Can you see the whiteboard?
Yes.
Yes.
Yes,
So
yes,
please,
yes.
please switch off your microphone. Switch your microphones off. Okay. Okay. So last time we considered statements which are just models for indicative sentences. Every statement is either true or false, but not both. We also considered connectives. A connective is such a way to combine two statements that the truth value of the compound statement is dependent solely on the truth values of these parts. Say A and B is true if and only if A is true and B is true, or one can state it the following way. Assume that if the value of A equals X and the value of B equals Y, then one can say that the value of the conjunction thereof of these two statements, A and B, equals what? Say X multiplied by Y. Do you agree?
Yes.
So the value of the compound statement can be computed from the values of its parts. Besides that, we introduced two notions. That of tautology. What is a tautology?
And
It's true.
that one, that's always true.
A tautology is a compound statement built from, say, A1, AN, such that it is true for whatever values of A1 and AN. Is it clear?
Yes.
Mm-hmm. And what does it mean that two statements are logically equivalent?
They are
That they have the same, yes, the same
Okay,
true or
okay,
false meaning.
okay. Their values, their truth values, it is not meaning, it is value, because meaning is something philosophical, and their meanings might be quite different. Say the statement 0 equals 0 is true. Hence, it is equivalent to the statement of Fermat's last theorem, but their meaning is their meanings are quite different. Anyway, so two statements are logically equivalent if and only if their truth values are always the same. And now let's state it and prove some theorem or lemma connecting these two concepts. So I say that F is equivalent to G if and only if the following formula F implies G and G implies F is a tautology. What do you think about that? So it is possible to express logical equivalence in terms of tautologies. Okay, let's prove it. First of all, let's consider a proof table for this formula. So F implies G, 0, 0, 1, 1, 0, 1, 1. F implies G. What is the table?
oh,
1,
1,
1.
0, 1.
1, 0, 1.
1, 0,
0,
1.
0,
Okay,
1.
okay,
Yes,
okay,
yes,
okay, thank
nice,
you.
nice.
What about G implies F?
1,
1,
0, 1, 1, 0, 1.
Surely. And what about
Yeah.
the conjunction of the two?
1, 0, 0, 1.
1, 0, 0, 1.
Ah, here we see that we have 1 if and only if the values of F and G are equal. So what does it mean? That this thing is a tautology. That means that the values of F and G are always equal. That is, they are equivalent. Is it clear?
Yes.
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 I
Yes.
hope it is quite clear. But anyway, if you have a question, please ask. On the other hand, it is possible to express being a tautology in terms of equivalence. Namely, F is a tautology. It is a tautology if and only if F is equivalent to some special Boolean connective T. T is a constant truth. It is the constant truth. So it is a connective which is always true. As a connective, it takes 0 arguments. So it is identically true. And likewise, we have bottom, which states for not true or for falsity. Is it clear?
Yes.
So when
Can you repeat, please, this statement?
when F is a tautology, if and only if it is equivalent to some truth. Is it clear? Okay.
It
Yes.
is.
Thank you. Now, our next step would be, let me think about, should we consider arguments and so on? No, let's skip it. Our next step will be predicates. Okay, predicates. By the way, that's funny, but as a noun, this word must be pronounced this way, predicate, not predicate. Curiously. But anyway, as a verb, it is still predicate. I want to predicate that. I want to say that, to say something about something. Okay. First of all, we resort to our first example about our old good friend, the quick brown fox. So, what does it do? The quick brown fox does what? It, do you remember?
Jumps
over the lazy dog.
Jumps over the lazy dog. Of course, here we have no connectives, but so it is an atom in terms of our seminar. But now let's split this atom. Let's analyze it and found here a subject. What is a subject here? A subject, it is the same as подлежащее.
Fox is fox, yeah.
It is fox. It is fox, or maybe the quick brown fox. You can name it the subject group. A quick brown fox. Who does what? The quick brown fox jumps over the lazy dog, and the lazy dog is can be called an object here. So here we have a subject. Grammatically, we have here a subject, a predicate, and an object. Who does what to whom? Subject does something to object. But I want to glue this together. I'll call this whole thing a predicate. And now let's do some abstraction work. The quick brown fox does something, jumps over the lazy dog. But can somebody else do the same thing? Namely, jump over the lazy dog.
Yes,
Who can?
Horse.
I can.
Of course.
Everyone.
Everyone. Okay. Say you can jump over the lazy dog, but it can be dangerous. That lazy dog might be not that lazy. It can bite you. But anyway, X jumps over the lazy dog. What is that? It is our predicate itself. If we substitute some appropriate name for X, we will obtain a statement. This one is not a statement. Why? Because
we don't have objects.
Whether it is true or false depends on X. So if you substitute a name for X, then you will obtain a statement. Be it the quick brown fox or somebody else, if you substitute a name for X, you will obtain a statement. Is it clear?
Yes.
This predicate has one argument. It has one argument or one variable. So But we can take one more abstraction step and consider something like that. X jumps over Y. It will be still called a predicate. But how many arguments do we have now?
2.
2.
Mhm. With 2 arguments. They are X and Y. So in general, what is a predicate? If you want a definition, of course, still informal, you can say something like that. A predicate is an expression, or better, let's fix the variables. Predicate with arguments, with variables. With variables x1, xn is an expression which turns into a statement when x's are when some names, when some appropriate names are substituted for x's. Is this idea clear? So a predicate is a statement with a parameter or more than one parameters. Is it clear?
Yes.
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 Okay, and now let's consider more mathematically looking examples. Say x equals 3 plus y. It is still a predicate. How many arguments does it have?
2.
2 arguments. For that reason, it is called a binary predicate. Binary for 2 arguments.
But here, one argument depends on the second one, so...
What do you mean by depend on? You want to say that for every x, there exists exactly one y. Maybe.
Yes.
But in fact, this doesn't matter. Sometimes it is true, sometimes it is false. So whether this one is true or false, or is it true or false? What is the main idea? The main idea is that this depends on x and y. So a predicate is an expression which turns into a statement which is either true or false if you substitute something for the variables. Is it clear? Let's consider substitution. Say we substitute 3 for x and 9 for y. Then we obtain a statement 3 equals 3 plus 9. It is a statement. Is it true or false? Hey, is it
It's
true
a
or
false.
Of course, that's false. And what if we substitute, say, 7 instead of x and substitute 4 for y. Then it is
That's true.
7 equals 3 plus 4. This is a true statement. So the truth
Yes.
depends on the substitution. But what if we substitute something just for x? We substitute, say, 1 for x and obtain thus 1 equals 3 plus y. Is it a statement?
No, it's still a
It's a
predicate.
predicate.
No, it is a
No.
predicate, but with one less argument. So it is called a unary predicate with exactly one argument. Is this idea clear?
Yep.
Of course, in mathematics, we have many predicates and say, you know, various equations, inequalities, and something like that are nothing more than predicates. Predicates are widespread and I dare say omnipresent, and they are very important. Besides the word predicate, we will use as a synonym the word property, or in Russian, свойство. Property is exactly the same as predicate. Say one can say about a property to be even. Say x is even. It is a predicate, or you can say that there is a property to be even. Is this idea clear?
Yes.
Okay. Every predicate is associated with some domain. What is a domain? In fact, domain is the domain of objects whose names can be reasonably substituted for variables. Say, does it make sense that 3 jumps over 4? Does it make sense?
No.
No.
No, probably not. This makes no sense. And what if I say that the quick brown fox is even? Does it make sense?
No.
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 But what if I say that 3 is even? Does it make sense?
Yes, and it's false.
Yeah.
Yes.
Yes.
It does make sense. Yet, it's false.
Oh, well, can I ask a question?
So, please.
Well, we, as I understood, yes, 3 jumps over 4, it makes no sense. But what if we will try to write a statement like 4 is divided by 0?
4 is divided by 0. What do you mean by is divided? Is divisible.
It's
If you mean divisibility, then this makes perfect sense. Here you want to consider, to exploit the following fact, that it doesn't make sense to divide by 0.
yeah.
But this is not about predicates. It is about names, about something like nouns. So the noun 3 over 0 denotes nothing. So as a noun, it makes no sense, but it is not a predicate. It is something. Predicate is a sentence with parameter, but this is a name for an object. It is not a sentence.
But maybe like x is divided by 0.
x is divided by 0, or better, 3 is 3 over x. 3 over x. It is a name form. It is a name form.
Okay.
So it is a name with perimeter. Some substitutions are such that it does not make sense. Some other substitutions are legal. So, but it is not about predicates. It is about names.
Okay.
You know, in the natural language, we have nouns and we have verbs.
Yes.
Predicates are like verbs, and these names are like nouns. We don't want to consider them now. Okay.
Okay.
So the domain. So for every predicate, there is a reasonable domain. So X is even. What is a reasonable domain? What is the set where one can reasonably take X from?
All the even numbers.
No. Not even, not only even numbers, but any number. For any number, or at least for any integer number, Sally, for any integer number, it does make perfect sense to say that that number is even. Of course, 1 is not even, but saying 1 is even makes sense. It is just false. Is this idea clear?
Yes, but
Yes.
I have a question. Why can't we tell the same thing about real numbers?
It depends. It depends on your convention. Probably it is. It also makes sense. Why not? Of course, this question about the domain is somewhat undefined, undetermined. So
So I have a
this
question.
is,
Can I? So domain is the sphere like where it will be make sense, yeah?
Of course. We
Yeah,
can
okay.
take objects whose names are substituted for X from. So something like that. X equals Y multiplied by 7. What is the domain? Probably numbers. Any objects for which you can reasonably talk about multiplication and multiplied by 7. Okay, what else? X is parallel to Y. What is the reasonable domain?
X and Y are vectors, so maybe some lines.
Lines or planes or something like that. Do you agree?
Yes.
Yes.
Yeah.
Yep.
And what about jumps over?
Some creatures, maybe.
Maybe
Yeah,
situations.
something alive. Something alive.
Something
So
named.
for X, something
For
that
example,
can jump. Maybe live creatures, of course. And for Y, anything that can be jumped over. So real objects, not abstract. So it doesn't make much sense to jump over 3. Is this idea clear?
Yep.
Yes. Yep.
So
Yes.
now we have two things. First of all, every predicate is associated by some domain. Even that association might be quite ambiguous. And after an appropriate substitution, a predicate is turned into a statement. Okay. Now we can see that it's possible to combine predicates using our connectives. First of all, let's do this thing which is familiar for every mathematician. Let's analyze the degenerate case. What do you think about the following idea? A statement is a predicate with 0 arguments. You know, a predicate with n arguments, which might be called n-ary predicate, it turns into a statement when x's are replaced by n names. But what do you think about a statement? A statement might be perceived as nullary, as the nullary predicate. Is it clear? It turns into a statement after substituting names for 0 variables. Does it sound logical?
Yes.
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 So we can generalize. A statement is also a predicate, but just with 0 variables. Okay. And now we can use the connectives to combine not only nullary predicates, but any predicates. Say x is even, and it is not the case. It is not the case that x. It is not the case that x plus y equals 3 multiplied by z. It is a predicate. How many variables does it have?
3, x, y, and z.
Okay. Is it clear? From this point of view, what is a system of equations or inequalities? What is a system? Or in Russia, you know, we use совокупность as well.
Well, I guess that
What is that? Is it a predicate?
yes.
Most surely it is built using connectives from some simpler predicates.
So this is a predicate with 7 variables, yes?
Why 7? Let's count the first, the second,
3.
the third, just 3.
Okay, understood.
Can I have a question?
Notice that identical names stand for identical objects. So please. What is your question?
Are all of them combined is a predicate, or pieces of them is predicate?
Of course, the subformulas are predicates as well. Of course, this conjunction is also a predicate. Why not?
Oh, thanks.
Okay, and now we want to consider something new. Clearly, every connective is a function which transforms predicates. Say, what negation does? It takes n-ary predicate. It takes n-ary predicate and transforms it. It maps it into which predicate? Oh, assume that there was x is even. No? you can transform it. It is not the case that x is even. Has the number of arguments changed?
No.
No.
It is the same.
And what about conjunction? Conjunction takes two predicates. Yeah? One predicate with n arguments and another predicate with m arguments. It is for times, for multiplication, and how many arguments in general will
n multiplies m?
no way, no way. Let's
N
consider
plus
an
m.
example. X is
2
even,
n
x is even, and x plus y equals 7. Here we have one argument. Here we have two arguments. In general, we will have no more than 1 plus 2 arguments. Maybe less, but no more. Do you agree?
Yes.
Yes.
But there are arguments with the same name.
So here we have just 2. Here in general, we have 2 arguments because this x is the same as this one. It is the same.
It's like less or equal n plus
Less
n.
or equal. In general, we do not insist that n predicate really contains all n variables, but no more than that. Is this idea clear?
Yes, it's clear.
But is it possible to lessen the number of arguments when constructing new predicates? It is. And one can call these transformations quantifiers. So what is a quantifier? Quantifiers. Quantifiers. In Russian, they are called kvantere. So it is not similar to the English word. Quantifiers. So what is the main idea? Say we have a predicate. X is even. By the way, may I write even of x instead of x is even?
Yes.
Yes, you
Is this
can.
idea clear? Okay. Assume that I have a predicate even of x, saying, of course, that x is even. And now I want to make the following transformation. There exists x such that it is even. So here we have how many arguments? One argument.
Wow.
And this is a statement. It is a statement. It doesn't make sense to substitute something for x. X is bound here. X is bound here. This expression binds x. Is this idea clear?
What do you mean by bound?
I mean that no substitution for x makes sense now. This variable is bound. Переменная связана. Не имеет смысла делать подстановку вместо нее. We have obtained a statement that is nullary predicate. Is it clear? Okay,
Yes.
let me elaborate on these bound variables. Let's consider your calculus course. do you have something like that? Limits.
Not yet.
No, not yet.
But in general, do you know what this expression stands for?
Yes. Yes. Yes.
Yes.
Yes.
It is the limit of a sequence. You know this limit equals 0. But does it make any sense to ask what is the value of this expression for x being equal to something?
No.
No.
Doesn't matter.
It
It's a
doesn't.
constant.
It doesn't. This variable is bound. Another example from calculus. Primitive function or integral. Do you know what it is? At least in general.
Yes.
Yes. Yeah.
So no sense in substituting something for x. X is purely syntactical. It is bound, so no substitution is possible. Likewise here, here we have one argument, and here we have no arguments. We have obtained a statement. Is it clear?
So quantifiers, it's like the statement only with one argument. And
Quantifiers in general, quantifiers decrease the number of arguments. So there exists, say it takes n plus 1 predicate and returns n predicate. Is this idea clear? No?
Can you show the example, please?
Quantifiers are making less predicates, yes?
Less arguments.
Less arguments, yes. Okay.
They diminish the number of arguments. In fact, I don't insist on this definition, for it is too lax. I'd better give you more examples. So x is even, and we can construct there exists x such that x is even. Another quantifier goes as follows. So our starting point is x is even, and I can say that for all x, it is true that x is even. Here we have one argument, and here no arguments at all, a statement. Is this idea clear?
Yes, it is. Yeah.
What else? In fact, there are many more quantifiers. Say there exists infinitely many. Infinitely many x such that the majority, whatever it means, the majority of x are such that, and so on. Is it clear?
Yes.
So like for all x, even x, it's like we're taking even x like to be true. Yes.
Like what?
We're taking even x like to be true always.
Why always true? Here, of course, here we say that all x's are even. That's false for the domain of natural numbers, yet it does make sense. So, two quantifiers are most important. The most important quantifiers are the following one. So, the most important quantifiers. These are the existential one, the existential quantifier. In plain English, it is something like that. There exists some x such that some a of x holds. In symbols, we will use the following notation. There exists x such that a of x, or simply there exists x such that a. Is it clear?
Yes.
There are many other ways to put it in words. Say, you can say for a suitable x, a of x, or there is an x such that. Or something is a, something is even say, or many other ways. Is it clear?
Yes, totally.
Yes, so these existent files are showing the existence.
The existence.
Yeah.
Whence the existential quantifier, existential.
And it can be expressed in the natural language way, like
There exists some x, of course. Sure.
And in this symbol, and it's possible to express via symbols.
Of course, there are other natural language expressions with the same or very close meaning. Okay, universal quantifiers. The universal quantifier is as follows: for each, or for all, for every, for each x, it holds that a of x. A of x is true for each x from some fixed domain. In symbols, we will use the following sign, or simply this way. Is this idea clear?
Yes, totally.
So for all x, a of x, for every x, for an arbitrary, для произвольного, for an arbitrary x, and so on. Is this idea clear?
Yes.
What about the meaning, the semantics of quantified statements? The truth depends on the domain. Let me write this down. The truth depends on the domain. Let us see an example. First of all, x is less than y. What is it? Is it a predicate?
Yes.
How many arguments does it have?
Two arguments.
Two arguments. Okay.
Two arguments, yes, two arguments.
What if I bind one variable with a quantifier? Say there exists x such that x is less than y.
It's
Now
simply
x is bound. It is a predicate with how many arguments?
One.
With
One
two,
argument.
one.
No, one argument. This is bound.
What about Y? What about
Y,
this Y1?
Y is free. Y is free. X is bound.
So we count the bounded arguments.
We can bound it, but if we do, then it will be a statement, not a one argument, not a unary predicate.
I see.
Let's bound it. For every y, for each y, there exists x such that x is less than y. Now we have a statement or nullary predicate. Is it clear?
I have a question. So we've made from the first predicate another predicate with one argument which is bounded, and then we've made a statement.
No, x is not y is not bounded here. Y is free. X is bounded.
Yeah, I said x is bounded and y is free.
Y is
unbounded.
free. It is
then,
still an argument. Y is an argument. And here we have no arguments.
So where y is an argument, this is a predicate, not a statement.
Yes, it is not yet a statement. It is a predicate with exactly one argument.
So
it
we can
says
tell that
for some argument y, for y, there exists a lesser number.
I mean, when can we tell that our thing is a statement where there are no
free variables?
Okay, thank you.
So it is a statement. All variables here are bound. And is this statement true or false? This depends on the domain. Assume that we are speaking about natural numbers. What if the domain is naturals?
Well,
it's true.
Is it true that for every natural number y, there exists a lesser number?
No, for one. No.
No, that's false because there exists the least natural number. Do you agree?
Yes.
And what if the domain we have chosen is the set of all integers?
Then it's true.
Then it is true because you know for every integer number there is a lesser one, say y minus 1. You can take for x y minus 1. Do you agree?
Yeah.
So the truth of the quantified statement depends on the domain. Is it clear?
Yep.
Okay, now let's express some other popular and important quantifiers in terms of these two basic quantifiers. First of all, they are mutually expressible. What does it mean that for all x's in some domain, a of x holds? This is true if and only if there is no such x in this domain that
Aotic.
all unicorns are tame. What does it mean? There is no unicorn
without
which is not tame.
Which is not tame, yeah.
So the universal quantifier is expressible in terms of the existential one. Is it clear?
Yes.
And
could you repeat, please?
What does it mean that all x's satisfy A? That means that it is not the fact that there exists x which does not satisfy. All unicorns are tame. Все единороги ручные. This is equivalent to the following. There is no unicorn which is not tame. Не существует единорога, который не был бы ручным. Is it clear?
Yes.
Likewise, there exists x such that A is true for that x. How is it possible to express it in terms of the universal quantifier? It is not the case that
For all x's, we will not find the A that will.
it is not the case that for every x, A is false. It is not always false, hence at least once it is true. Is this idea clear?
Yes.
Yes.
Another popular quantifier is as follows. There is a unique x such that A of x. Usually symbolically, it is denoted the following way. There exists just one x with the property A. How is it possible to express it in terms of other quantifiers? There exists x with the property A and существует единственно. There exists a unique x such that
For
X
any x,
or
which
any y, if y also satisfies A, then y is the same as x. Is it clear?
Знак восклицания, it means that it's x is unique.
It means that x is unique. This is quite usual notation, both in Russian and in English. Isn't it familiar for you?
It is more familiar that exclamation mark means not.
No. In this context, it means there is a unique x.
Okay.
Maybe in calculus course, you will see examples of this kind. Okay, so there is no need in new quantifier in order to say that there is just one x with some property. Is it clear?
Yes.
yes.
Another thing I want to discuss is so-called vacuous truth. It is also very frequent situation. Vacuous truth. What is a vacuous truth? Okay, let's see. Let's consider the following phrase. The present King of France is bald or hairy, if you wish. The present King of France is bald. Is it true or false?
Depends on if they're king in France.
And is there a king?
Yeah,
What
if
do
they're
you
king.
think? There is a king.
France,
Who
we
is
don't
the king?
No.
We don't have
There is
France.
What about the Fifth Republic? Oh,
No,
excuse me,
okay.
Republic.
If you had a king.
I guess they have a president.
No, present.
We don't have king in the
So
France.
it's false.
It's false
Ah.
because they don't have a king.
Yes.
No king, just La République. Le Marseillais, and
Actually,
something
it's
like
true.
that. Why? Why is it true?
Because we can prove it by using that for there exists such x like
If there exists such X, who is the king? It should be false.
we can, no. I want to say that we can prove that not for any like using equalities 1 or 2. I should choose one of them. Do you understand?
No, I haven't.
1 second.
Does it depend on the domain?
On the domain is all people who have ever lived. But first of all, let's express it in terms of quantifiers. The standard way to present such things, to render them mathematically, is as follows. For each x, if x is the present king of France, if x is the present king of France, then x is both. This is the standard way. If we follow this standard way to render things mathematically, then we have to acknowledge that this assumption is false for every x. If you care about the domain, so the domain is the humankind. Everyone, no one is the present king of France. Do you agree?
Yes.
Yes.
And if as the assumption is false, then the implication
Is always true.
it is always true. So this one must be considered true. So if we say something about non-existent objects, if we want to say that every non-existent object satisfies some properties, then it is true. Another example, every round square, is there any round square, круглый квадрат?
No.
Every round square is round. Does it sound logical?
Yes.
Yes.
Of course. So it is true. That's true. By the way, if I say that every round square is not round, it will be no less true. For there are no round squares. Is it clear?
So if argument doesn't make sense, it's always true.
No, if x does not exist. So I say that for each x, if x is a round square, which is not possible, this is a predicate, it is either true or false, but it is always false, then x satisfies some property. As this one is always false, then for every x, then this implication is always true. Is it clear?
Yes.
Yes.
Such a situation is very common in mathematics, and it is known as the vacuous truth. When something is true for the field, the area, the domain or subdomain of these objects is empty. That is, it is vacuous. Now let me elaborate even more on this topic. And I want to introduce so-called bounded quantifiers. Of course, this word is not very nice here because we have bound variables. But nevertheless, this is a standard term. So we have not much choice. So-called bounded quantifiers or ограниченные кванторы in Russian. So what is the main idea? Bounded quantifier is something like that. Let A be a subset or a set. Do you know intuitively what is a set? What a set is?
Yes.
Let A be a set of objects from the domain. Some subset, some subdomain. Then we can use the following expression. For every x from A, or A, we have used A previously. What do you think about Greek letters? Do you like them?
Yes.
I think it is cool.
Yes, yes.
You even
We need them in our life.
if you don't like them, you cannot avoid them. So for every x from A, phi, not phi, phi of x holds. What does it mean? By definition, that means that for every x from the domain, if x belongs to A, then phi of x holds. This is by definition. Likewise, there exists x from A such that phi of x holds. What does it mean? That means that there exists x such that x belongs to A. Please notice the different connective. Here we have not implication, yet conjunction. There exists x which indeed belongs to A, and also it satisfies phi. Is it clear?
I guess.
So
Yes.
what is the situation of vacuous truth? It happens when A is empty. When A is empty, we have something like that. For each x, if x belongs to the empty set, then phi of x. Can anything belong to the empty set?
No.
No.
True.
So this assumption is false, whence the conclusion is always true. Is it clear?
Yes, I have a question. Can you show, please, about when we said about the Kim, your statement? There is induction.
No,
Yes?
induction, why?
Ну, там вот значок следствия, а там же должно быть или все правильно.
Implication.
Ой, induction, говорю, implication, да.
Implication, yes, but these two signs mean the same.
Okay.
They both mean implication, but I'll use them depending on the context. But you may use freely the one you like more.
Okay, thanks.
So let's consider this statement. There exists x which belongs to the empty set, and also besides that, it satisfies phi. What can we say? This is false. Is it clear?
Yes.
Yes.
But why the set is empty?
What if it is empty?
Okay.
So like the set of all present kings of France. There is no king in France presently. Is it? Or is any? So is it clear?
Yes.
So for the kings of France, we use the first statement, yes? For all.
Yeah.
But we don't have...
Why do we do so? We don't want to say that there exists a king. We say that everyone who is a king, he is bold. So this is the key. That the fact that X is the king of France goes into the assumption. And it is very logical, in fact. And now, in order to see why it is so logical, let's do some easy exercises in translating natural language meanings to the mathematical language. Okay, let's translate using quantifiers. Every human is mortal. Every human is mortal. How would you translate it into quantifier language?
I guess for all x.
For all x from some domain, if x is a human,
yeah.
If x is a human, then
x is
mortal. Do you agree? Is it logical?
Yes.
Yes.
And the scheme, the pattern is exactly that as here, where we talked about round squares. Every round square is rounded. Every x, which is a round square. Every x who is a human is necessarily mortal. Is it clear?
Yes. Yes.
What else? Every natural number that is divisible by 4 is divisible by 2. So please.
For all natural numbers, brackets.
For all x, or maybe for all x from the set of naturals.
X is divisible by 4, implied that x is divisible by 2.
No. Not every x is even.
There are two variants, I think. The first one is for all x.
Not every.
There is like this.
This one is literal. It is a literal translation, but we can use this these equivalences, and we can in fact move the negation sign into the quantifier scope. So we can say that it is equivalent. There exists x,
but is
which is not
even.
Which is not even. Is it clear?
But we can also write like x is not divisible by 2, just because.
Of course, because even of x is equivalent to x is divisible to 2. Surely. Everyone loves himself.
It's false.
Maybe, but can we state it in quantifier language? We can use the following predicate, L of x and y. X loves Y. So, and what is the translation of the whole phrase?
For all X.
For all X,
L
Love
of
XY.
X and X.
yeah.
Do you agree?
X and X?
Of course. He loves himself.
Ah, okay, yeah.
Isn't that logical? Someone is loved by somebody.
He will have L X by.
And what are X and Y? This is a statement. It is either true or false, but here we have parameters, free variables.
There exists such X and there exists such Y that L.
Surely. Is it clear?
Yes. And it will be bounded, yes?
What's bounded? X is bound.
Okay, bound.
The quantifier binds, you know, in English we have bind, bound, bound. It is an irregular verb meaning связывать. But bounded is a derivative from this word. Bound is связь, ограничение, while bounded means ограниченный.
Okay.
Okay, so let me continue, for we have some time and there is no reason in beginning the new topic now. So let's, we'd better do more exercises. Some key can unlock, every door. What do you think?
There are two parameters, key and door.
Yes.
Of course, we can.
And there exists door.
For every X, there exists Y, but let's say that X is a key.
Then it exists.
Excuse me, exists.
Exists.
There exists X, which is a key, such that
For any door.
Y. How could I filter out just doors from the domain? What is the right idiom here?
Or open Y maybe.
Of course, X equals X opens Y, but how is it possible to say that Y is the door?
Then write Y door.
Just
Of
write
course,
door
but
in Y.
The main
Door
idea
physics.
is that it is it goes into the assumption for every Y, if Y is a door, then is it clear?
Yes.
Yes.
We write open as a function. Yes.
Open is a predicate, predicate or better, of course. Opens X, opens Y.
Oh, okay.
It is a much like jumps over. X jumps over Y or X opens Y.
I have a question. Why does exists X in the outer bracket from the rest of the expression?
In the outer bracket, so we have something like that. This quantifier binds this occurrence of X and this one alike. There are two occurrences of X. Or what is your question?
I see, yeah.
Okay. Therefore, every door, okay, another phrase, every door, by the way, if we fix the domain of X to be that of keys, we can skip this part, we can omit it. Every door may be unlocked with some key. every door may be unlocked with some key. Let's translate it into mathematical language. What is the first quantifier?
For any, for all.
For all x, what's next?
Door X.
Door x, but what is the right connective?
Exists. No.
Like arrow.
Implication.
Implication.
Whenever x is a door, if x is a door, then
Open.
Exists.
Then exists.
there
Exists.
exists some y,
If
Which
y
opens door.
which is a key.
Why?
It is a key.
And
And
open.
opens.
and
The
open.
door.
It opens the door. What about the brackets? Okay, now everything must be okay. So is it clear?
Why we use multiplication k and opens?
You mean conjunction?
Yeah, conjunction.
Conjunction. Because we state that there exists an object which is a key and opens the door. You know, may be unlocked with some key. There exists what? Some key which does what? Opens the door. Or isn't it logical?
It's logical.
Okay, okay. So, by the way, is it true that whenever this one holds, then the second statement holds as well? By the way, it would be better to rename bound variables so that their, say, type is the same as previously. Y stands for doors and X stands for keys. Interesting. Is it always true that when this one is this one holds, the first one holds, then the second one holds as well? Is it true? What do you think?
Well, arithmetically it does, but logically I think it is a difficult question.
Arithmetically, so that's quite curious. So you can prove it using some arithmetical computation, even though quantifiers range over the infinite domain. So it is not possible to construct a truth table for quantifiers in general.
I guess they are not similar.
They are not similar, they are not the same, but is it true that the first one implies the second one? Let's think about it informally. There is a universal key which can open every door. Is it the case that every door can be opened, can be unlocked with this universal key?
Yes.
Yes.
Okay,
Yes.
so we can prove that this one, the first one, implies this one. Why is it so? Let's take this key which exists and apply it to whatever door we are given with. We know that this key you can denote it with x0, say, or x prime. This key, this universal key, opens every door. So whatever door is given, it will be unlocked with this universal key x prime. Does this sound logical?
Yes, I guess.
Of course it is. It is like a law of logics, but not a law of connectives, but a law of quantifiers. It is not called tautology, but this formula, this implication is universally valid. That means that the truth of this implication does not depend on what do we understand by keys, doors, and opens. But of course, this matter is quite complicated. It is the realm of logic itself, of mathematical logic, of first order logic, and we are not going to consider it in any detail. And let's just restrict ourselves to considering this implication. Is this one universally valid? Is it true that if for every door we have an appropriate key which can open it, then there exists a universal key opening every door?
No, it's
No,
not.
it's obligatory.
No, it is not necessarily so, because it is possible we can model the following situation when for every key we have just a unique, excuse me, for every door we have its own key opening it, yet no key opens every door. The simplest example of such a situation is as follows. We have two doors with distinct keys opening them, but key for the door A cannot unlock the door B, and vice versa. Is it clear?
Yes.
Formally describing such a situation means constructing a model where one formula is true and the other one is false. This way, in mathematics and mathematical logic, we can disprove some implication. We can construct a model where the assumption of that implication is true and the conclusion is false. But the formal analysis of all such situations is quite involved technically, and in fact is out of the scope of our course. We will stick to informal treatment, to the informal treatment of logic. So we will more use it than study it. Any questions, please?
I'm trying maybe to understand how we can count arguments. Well, I just maybe was a bit.
How many arguments does a predicate have? Of course, it is this your question? Or what?
I guess so, yeah.
How many arguments? Practically the simplest way, when you have some expression with variables, is to count the number of distinct variables. While one variable can have more than one occurrence. So you can say that x equals 7 multiplied by y, and x is less than z. Here, the same x has two occurrences. We want to say that some x, some distinct object x, satisfies two properties.
Yes.
So here we have three arguments, as we have three distinct free variables.
So variables, these are x and y.
X, y, and also z.
Z, I see. Yes, that's it. Well, then I see.
Okay, thank you. What else? Any more questions?
You mentioned that we're going to use informal rule of logic. What does that mean?
Of course. Something like that. This is an example. By the way, we haven't proved that formally, but we will freely do such a transformation in our developments, in our proofs.
Okay, thank you.
Or we will, for example, assume that this formula, like that from the example with keys and doors, for every x, there exists x such that for every y, phi of x and y. X opens every y. This implies that for every y, there exists x such that phi of x and y. We will assume that this one is universally valid. That is for whatever phi, for whatever domain. We will use such things as we usually apply them in our informal proofs, as you have done previously in your high school experience or else. Is it clear?
Yeah,
Totally, yeah.
So logic is a part of our mind. We don't want to analyze and formalize logic too much, but we should surely we must use it. We have to use it because logic is the only available instrument, only available tool to prove theorems, isn't it?
Yes, sure.
We will use intuitive truths of logic like this one to prove theorems of mathematics. Any more questions?
Are you going to publish this concept somewhere?
Do you mean this whiteboard image? By the way, I can send it via our chat here.
Thank you very much.
Or can we see the everything what was in lecture by
I've sent it, by the way.
Yeah, okay.
So thank you.
Thank you.
Thank
This
you
lecture
very
was
much.
amazing.
Thank you.
Goodbye.
Thank you pretty much.
Goodbye.
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 Bye.
Goodbye.
Bye.
Thanks.